Part 1. The Anomaly. Something is wrong with Comet 3I Atlas. In the cold darkness of the inner solar system, it defies every rule we thought we knew about comets. Its three distinct tails, an ion tail, a dust tail, and an antitail, point in different directions, a configuration that shouldn't persist this long after perihelion. The antitail, a sharp beam of light directed toward the sun, should have faded weeks ago. Instead, it's sharper, more defined than ever. We're 32 days from the comet's closest approach to Earth, and astronomers worldwide are scrambling to explain what they're seeing. But the more they look, the more questions arise. This isn't just an unusual comet. It's a challenge to our fundamental understanding of how these icy wanderers behave. The image that sparked this investigation came from a 2.6-meter telescope in Rayong, Thailand, operated by Tiasak Talawang. The resolution is exceptional, the processing clean. What it shows is impossible. Three tails, each clear and distinct, defying the timeline astronomers expected. The ion tail, a thin bluish streamer, is pushed straight back by solar wind. The dust tail, broader and curved, follows the comet's orbital path. And then there's the antitail, a spike of material pointing back toward the sun, as if defying the very forces that shape it. This isn't a blurry photo or an amateur's lucky shot. It's a precise observation that has veteran comet watchers using words like unprecedented and unexpected. And when people who've seen hundreds of comets over decades start using those words, you pay attention. Tiasak Talawang's telescope, housed in a modest observatory nestled among the rolling hills of Rayong, has become a focal point for global astronomical interest. The instrument, a state-of-the-art reflector with a 2.6-meter mirror, has captured images that rival those of larger, more famous observatories. The clarity of the Thailand images has allowed astronomers to measure the angular width of the antitail with unprecedented precision. Early estimates suggest it is less than 0.5 arc-seconds wide, an astounding level of collimation for a feature that should be dispersing chaotically. The images have been independently verified by teams at the European Southern Observatory and NASA's Jet Propulsion Laboratory, eliminating any possibility of error or artifact. Why does this matter? Because comets are predictable. They follow patterns established over centuries of observation. We understand the physics. Solar radiation pushes dust away, solar wind strips ions and carries them downstream. When Earth crosses a comet's orbital plane, we sometimes see an antitail, a temporary illusion where large dust particles seem to point sunward. But those antitails are fleeting, fading within days or weeks as the particles spread out. 3I Atlas is 17 days past perihelion, and its antitail looks like it's been sharpened with a blade. If you compare images from early November to this Thailand observation, you wouldn't see decay. You'd see intensification. You'd see a structure organizing itself more tightly, more coherently, as if something inside or around this comet is actively maintaining it against every dissipative force that should be tearing it apart. The implications of this anomaly extend beyond the study of comets. If 3I Atlas is defying known physics, it could challenge our understanding of solar system dynamics as a whole. Comets are often described as dirty snowballs, remnants of the early solar system that have remained largely unchanged for billions of years. They offer clues to the conditions present during the formation of the Sun and planets. However, 3I Atlas is behaving in ways that suggest it may not be a typical comet. Its unusual tail structure could indicate the presence of unknown forces or materials, or it could point to a unique history that sets it apart from other comets. One of the most puzzling aspects of 3I Atlas is its trajectory. Unlike most comets, which originate from the Oort cloud or the Kuiper belt, 3I Atlas appears to have an unusually elliptical orbit. Its perihelion, the point at which it is closest to the Sun, is approximately 0.78 astronomical units, AU, well within the orbit of Venus. At its farthest point, or aphelion, it reaches beyond the orbit of Neptune, suggesting a highly elongated path. This orbit is not typical of short-period comets, which usually have more circular paths, nor is it entirely consistent with long-period comets, which often have more extreme orbits. The unusual orbit of 3I Atlas raises questions about its origin and whether it has been influenced by gravitational interactions with other celestial bodies. The anti-tail of 3I Atlas is not the only mystery surrounding this comet. Spectroscopic analysis of its composition has revealed unexpected elements. Preliminary data from ground-based observatories and the Hubble Space Telescope indicate the presence of compounds that are rare or unheard of in comets. Trace amounts of exotic ices such as nitrogen and carbon monoxide have been detected, along with unusual ratios of isotopes like deuterium and helium-3. These findings suggest that 3I Atlas may have formed in a region of the solar system far different from where most comets originate. Some researchers have even speculated that it could be an interstellar object, similar to Oumuamua, the first known interstellar visitor detected in 2017. However, unlike Oumuamua, which had a hyperbolic trajectory indicating it was passing through the solar system, 3I Atlas appears to be gravitationally bound to the Sun. The scientific community is abuzz with theories to explain the anomalies of 3I Atlas. Some propose that the comet's unusual behavior is the result of an internal process, such as a sudden release of volatile materials from deep within its nucleus. Others suggest that it could be interacting with an unseen companion, such as a small asteroid or fragment that is influencing its tail structure. Still others point to the possibility of external forces such as magnetic fields or solar flares playing a role. However, none of these hypotheses fully explain the persistence and sharpness of the anti-tail. The truth may lie in a combination of factors or in a phenomenon that has yet to be observed or understood. Observation: 3I Atlas displays a triple tail configuration 17 days post-perihelion, including an anti-tail that should have faded. The anti-tail is less than 0.5 arc-seconds wide, an unprecedented level of collimation. The comet's orbit is highly elliptical, with a perihelion of 0.78 AU and an aphelion beyond Neptune's orbit. Spectroscopic analysis reveals the presence of rare compounds, including nitrogen and carbon monoxide ices and unusual isotope ratios. Interpretation: the anti-tail's persistence and sharpness defy known cometary behavior, suggesting the presence of unknown forces or materials. The comet's unusual orbit and composition hint at a unique origin, possibly outside the solar system. Theories to explain these anomalies include internal processes, interaction with an unseen companion, or external forces. Speculation: 3I Atlas could be an interstellar object captured by the Sun's gravity, or it may represent a new class of comet with properties not yet understood. Its behavior challenges existing models of cometary physics and solar system dynamics, opening the door to groundbreaking discoveries. As the countdown to 3I Atlas's closest approach to Earth continues, the scientific community is mobilizing. Observatories around the world are training their telescopes on the comet, capturing every detail of its evolution. Space agencies are considering emergency observation campaigns reallocating resources to study this enigmatic object. Meanwhile, amateur astronomers, armed with increasingly sophisticated equipment, are contributing valuable data, proving once again that the pursuit of knowledge is a collective endeavor. The coming weeks may rewrite the textbooks, but for now the mystery of Three-Eye Atlas deepens, a reminder that the universe is vast, unpredictable, and full of wonders yet to be discovered. Part 2. The Timeline of Defiance. Three-Eye Atlas wasn't always defying expectations. Rewind to September, when the comet was inbound, approaching the Sun. Veteran observers like Michael Yeager began documenting the anti-tail's development, a normal phenomenon as Earth approached the comet's orbital plane. Yeager, a seasoned astronomer with over 30 years of experience, had witnessed countless comets behave predictably under the Sun's influence. Everything seemed textbook. The anti-tail sharpened, peaked around perihelion on October 29th, and astronomers expected it to fade as the comet moved away from the Sun. But it didn't. By early November, observers noticed something strange. The anti-tail wasn't fading. It was holding steady, even sharpening. Telescopes around the world began to turn toward Three-Eye Atlas, capturing thousands of images as amateur and professional astronomers alike tried to make sense of the anomaly. By November 10th, the Virtual Telescope project captured stunning images showing all three tails clearly defined. The anti-tail in particular was a revelation, sharp, linear, and extending farther from the nucleus than before. This wasn't a minor detail. The anti-tail stretched over 1 million kilometers into space, defying the expected behavior of cometary dust. Observatories from Hawaii to Chile began to share their data, revealing a pattern that was as beautiful as it was baffling. The anti-tail seemed to glow with an intensity that defied its composition, as if an unseen force were holding it together. The Thailand observations on November 13th and 15th brought the anomaly into focus. Tiasak Talawang's images showed an anti-tail that wasn't just persistent, it was intensifying. Talawang, working from a small observatory in Chiang Mai, spent hours meticulously adjusting his equipment to capture the comet's fine details. Comparing these images to earlier observations revealed a structure that seemed to defy the laws of physics. The anti-tail should have been fading, dispersing into the background of space as the comet receded from the Sun. Instead, it was sharper, stronger, and more defined than ever. This wasn't a subtle anomaly. It was a screaming data point that demanded explanation. The timeline itself became the evidence. Each date, each observation. A checkpoint where Three-Eye Atlas violated expectations. But why? What could explain this defiance? Theories began to emerge, each attempting to reconcile the observations with known physics. Astronomers across the globe convened in virtual meetings, poring over spectroscopic data and light curves. Some proposed that the anti-tail was being influenced by an unseen gravitational force, while others suggested that the dust particles were behaving in ways never before observed. But as we'll see, none of them fully account for what we're witnessing: observation. The anti-tail's brightness did not diminish over time. In fact, photometric measurements revealed that it was increasing in luminosity, despite the comet's increasing distance from the Sun. This suggested that the dust particles were either reflecting more light or were being energized by an unknown mechanism. Interpretation. One hypothesis posited that the anti-tail was composed of unusually large dust grains, which could retain their structure longer than typical cometary dust. However, This theory struggled to explain the sharpness of the anti-tail, as larger grains would typically disperse more slowly, but less uniformly. As the days passed, the anomaly grew more pronounced. By November 20th, the anti-tail had extended to over 1.5 million kilometers, visible even. In amateur telescopes, social media buzzed with images and videos as millions of people around the world marveled at the mysterious comet. The European Space Agency, ESA, and NASA both issued statements acknowledging the phenomenon, though neither offered a definitive explanation. The scientific community was divided, with some researchers cautioning against premature conclusions, while others embraced the possibility of a groundbreaking discovery. Speculation. Some astronomers suggested that 3I Atlas might be interacting with an unseen companion object, such as a small, undetected asteroid or even a dark matter candidate. This idea gained traction when simulations showed that such an interaction could explain the anti-tail's behavior, though no direct evidence of such an object was found. Meanwhile, the comet continued on its journey, seemingly indifferent to the chaos it had created. On Earth. By December, 3I Atlas was moving away from the Sun, its tails still defying the laws of physics. Astronomers continued to monitor it, hoping that time and distance would reveal the secrets of its enigmatic behavior. But as the comet faded from view, the mystery only deepened. Part 3. Theory 1. Massive dust grains. The most conservative explanation is that 3I Atlas is shedding an unusually large quantity of massive dust grains, particles a millimeter or more in diameter. These grains, too heavy for radiation pressure to push away quickly, would stay close to the orbital plane, creating the illusion of an anti-tail. The persistence we're seeing could simply be due to the sheer volume and mass of the particle population. There's precedent for this. Some comets are dustier than others, with higher ratios of solid particles to gas. If 3I Atlas has an internal structure that fragments easily, or if its approach to the Sun triggered extensive breakup, it could have released a substantial cloud of debris. For instance, Comet 67P Churyumov-Gerasimenko, which was extensively studied by the Rosetta mission, was found to have a dust-to-gas ratio of about 4, meaning it released 4 times more dust than gas. During its active phase, if 3I Atlas has a similar or even higher ratio, it could explain the dense, lingering anti-tail. However, the behavior of 3I Atlas is not entirely consistent with typical cometary activity. Most comets experience significant outgassing as they approach the Sun, with water ice sublimating into gas and carrying dust particles away. This outgassing usually peaks around perihelion when the comet is closest to the Sun, and then tapers off as the comet moves farther away. 3I Atlas, however, seems to defy this pattern. Observations from the Thailand National Observatory, situated atop Doi Inthanon, captured the anti-tail's sharp edges 18 days after perihelion, when the comet was already 0.3 astronomical units farther from the Sun. At this distance, solar radiation is roughly 20% less intense than at perihelion, yet the anti-tail remains distinct and well-defined. But there's a problem. Sharpness. If we're looking at a massive population of large particles spreading out over 18 days, we'd expect to see blurring. The anti-tail should be widening, its edges becoming more diffuse as individual particles drift at slightly different velocities and angles. Instead, the Thailand images show boundaries. The anti-tail maintains a relatively narrow profile. This suggests either the particles are being replenished, or there's some focusing mechanism keeping them columnated. Continuous replenishment this far past perihelion is hard to justify, as comet activity drops off as it moves away from the Sun. For example, Comet Hale-Bopp, one of the most active comets ever observed, saw its dust production rate drop by over 50% within just 30 days after perihelion. If 3I Atlas were following a similar pattern, its anti-tail should be fading, not maintaining its sharpness. The focusing mechanism hypothesis is equally perplexing. While radiation pressure pushes particles away, it doesn't focus them. There's no known natural process that would columnate a beam of millimeter-scale particles in this configuration. Some theories propose that magnetic fields could influence the trajectory of charged dust particles, but this would require the particles to maintain a charge over long distances, which is unlikely given the neutralizing effects of the solar wind. Additionally, the magnetic field of the Sun, which extends outward as the interplanetary magnetic field, is not strong enough to confine particles of this size and mass. Gravitational effects from other celestial bodies, such as planets or moons, are also insufficient to explain the focusing, as 3I Atlas is currently in a relatively empty region of space, far from any major gravitational influences. Another possibility is that the particles are not purely passive, but are interacting with one another in some way. For instance, electrostatic forces could cause particles to clump together, creating a more cohesive structure that resists dispersion. However, this would require the particles to be highly charged and to maintain that charge over extended periods, which is unlikely in the vacuum of space. Additionally, such interactions would likely result in a more irregular, clumpy appearance, rather than the smooth, narrow profile observed in the anti-tail. Observation: the anti-tail's sharpness persists despite expected dispersion. Unknown: the mechanism maintaining the narrow profile. Speculation: could there be an unseen companion body influencing the particles? Some comets, such as 67P, Churyumov-Gerasimenko, have been found to have binary or multiple nuclei which could create complex gravitational interactions. However, no such companion has been detected for 3I Atlas, and the likelihood of an undetected body exerting sufficient influence is low. The mystery deepens as we consider the implications of these observations. If 3I Atlas is indeed releasing massive dust grains, it challenges our understanding of cometary behavior and the mechanisms governing particle dispersion in space, the anti-tail's persistence and sharpness suggests that something unusual is at play, whether it's an unknown focusing mechanism, a unique internal structure within the comet, or an external influence we have yet to identify. As scientists continue to analyze the data, the enigma of 3I Atlas may force us to rethink the fundamental principles of comet dynamics and the forces that shape our solar system. Part 4. Theory. 2. Icy fragmentation. The second hypothesis suggests that Comet 3I Atlas's nucleus broke apart during or shortly after perihelion, producing large icy fragments. These fragments, acting as temporary mini-comets, would each have their own coma and tail. Their overlapping, outgassing plumes could create complex tail structures, including the enigmatic anti-tail. This theory has precedent. Comets do break apart, and the resulting debris fields can be spectacular. Comet. Shoemaker-Levy 9 famously broke into more than 20 fragments before impacting Jupiter in 1994, creating a dramatic string of pearls effect as it plunged into the planet's atmosphere over 6 days. The impact left scars in Jupiter's clouds that were visible for months, a testament to the destructive power of fragmented comets. If 3I Atlas broke into several large pieces, each outgassing independently, it could theoretically create the complex. Tail morphology astronomers are observing. However, fragmentation events are not always so clean or predictable. Comet 73P Schwarzmann-Wachmann 3, for instance, began fragmenting in 1995 and has since broken into more than 70 pieces, scattering debris along its orbit. The fragments vary widely in size and activity, making their outgassing behavior difficult to model. For 3I Atlas, the fragmentation theory suggests that each fragment would act like a smaller version of the original comet, releasing dust and gas as it warms in the sun's heat. This overlapping outgassing could, in theory, produce the intricate tail structures observed, including the antitail, which extends in the opposite direction of the main tail. Yet, the theory struggles to explain the sharpness and coherence of these features. The problems with this hypothesis are substantial. First, there's no direct evidence of fragmentation. Observers have been monitoring 3I Atlas closely using some of the most advanced telescopes in the world, including the Hubble Space Telescope and ground-based observatories like the Keck Telescope in Hawaii. While the comet's nucleus isn't resolved as a disk, it's too small and distant for that. Astronomers can measure its central brightness concentration with remarkable precision. If the nucleus had split into multiple fragments, we'd expect to see multiple brightness peaks, or an elongation of the central condensation. The observations, however, show a single compact nucleus. This lack of evidence is a major strike against the fragmentation theory. Second, the sharpness problem persists. If 3I Atlas's tail structures were the result of outgassing from multiple fragments, we'd expect to see irregularities, patchiness, and variations in brightness and structure. Each fragment would likely have its own outgassing pattern, influenced by its size, composition, and orientation toward the sun. The resulting tail would be a chaotic blend of these individual contributions. Instead, the antitail looks smooth and continuous, almost eerily so. It stretches across millions of kilometers of space with a uniformity that defies the fragmentation explanation. The main tail, too, shows a level of organization that seems inconsistent with the idea of multiple, independently outgassing fragments. There's also a timing issue. If fragmentation happened at or near perihelion, the point in the comet's orbit where it is closest to the sun, the fragment separation should be increasing over time. As the fragments move apart, their outgassing plumes would diverge, creating increasingly complex and chaotic tail structures. Yet, observations of 3I Atlas show the opposite. The tail structures are becoming sharper and more organized as the comet moves away from the sun. This contradicts the fragmentation theory, which predicts growing disorder, not order. Speculation. Could the fragments be outgassing in a coordinated way, perhaps due to their shared origin and composition? If they were all part of the same nucleus, they might behave similarly when exposed to solar radiation. However, this seems unlikely. Comet fragments often exhibit varied activity levels, as seen in the case of Schwarzmann-Wachmann 3, where some pieces outgas vigorously, while others remain relatively dormant. The idea of synchronized outgassing from multiple fragments is difficult to reconcile with observed comet behavior. Observation. The antitail's smooth, continuous structure remains unexplained. Its sharpness and coherence are at odds with the fragmentation hypothesis, which predicts a more chaotic and irregular appearance. The lack of evidence for nucleus fragmentation further undermines this theory. Interpretation. While fragmentation is a plausible mechanism for creating complex tail structures, The specifics of 3I Atlas's behavior suggest that something else is at play. The comet's tail features are too organized, too sharp, and too consistent with a single coherent source of outgassing. The fragmentation theory, while intriguing, fails to account for these observations. Unknown, the mechanism creating the antitail's smooth, continuous structure. If not fragmentation, then what? The search for answers continues. Part 5, Theory 3, Directed Jets. The third explanation invokes a mechanism we know exists but rarely see so persistently: directed jets from stable vents on the nucleus. If 3I Atlas has one or more active regions producing focused jets of gas and dust, and if the nucleus's rotation is slow, or the vent is located near a rotation pole, the jet could remain pointed in roughly the same direction for extended periods. The anti-tail in this model is a sustained jet that happens to point sunward from our viewing angle. Jets are real. We've seen them on many comets, including Comet Churyumov-Gerasimenko, where the Rosetta mission imaged jets erupting from the surface, some reaching speeds of up to 1,000 meters per second. These jets are driven by the sublimation of ices, particularly water ice, as the comet approaches the sun. The physics is sound. Jets can create sharp features and be sustained over weeks if the vent remains active. For example, Comet Hartley 2, observed by NASA's Epoxy mission in 2010, exhibited jets that produced a distinctive peanut-shaped nucleus, demonstrating the sculpting power of sustained outgassing. The jets on Hartley 2 were remarkably consistent, with some lasting for weeks, ejecting up to 220 kilograms of material per second and shaping the comet's environment in a dramatic way. But there's a challenge: rotational smearing. Comets spin, typically with rotation periods ranging from hours to days. As the nucleus spins, any fixed vent on its surface would sweep through a circle like a lighthouse beam. From our perspective, we'd see the jet appear, brighten as it rotates toward us, then fade as it rotates away. Over multiple rotations, this would create a fan-shaped or conical structure in the tail, not a narrow beam. For a jet to create a persistent, sharp, linear feature like the anti-tail, the nucleus would have to be rotating very slowly, or the vent would have to be located at the rotation pole, aligned with the spin axis. Both scenarios are possible but statistically unlikely. Slow rotation isn't unheard of, but most comets spin relatively fast due to gravitational stirring by planetary encounters over millions of years. Comet 1P Halley, for instance, has a rotation period of about 2.2 Earth days, while Comet 67P Churyumov-Gerasimenko spins every 12.4 hours. Having a vent precisely at the pole in an orientation that happens to create a sunward-pointing jet at this specific moment is a fortunate coincidence. Comet 29P Schwarzmann-Wachmann 1, however, offers a tantalizing precedent. It is known for its frequent outbursts and has a rotation period of about 14 hours, but some of its jets have been observed to persist for days at a time, hinting at the possibility of stable vents that could, under the right conditions, produce prolonged linear features. The directed jet theory also raises questions about the composition and structure of the nucleus. For a jet to persist, it would require a substantial reservoir of volatile materials beneath the vent. This could mean that 3I Atlas has a particularly ice-rich region near the surface, perhaps the result of a recent impact or a localized collapse, exposing fresh material. The sustained jet would also need to overcome the comet's gravitational pull, which, while weak, could still affect the trajectory of the ejected particles. For instance, A jet from a comet with a diameter of 10 kilometers would experience a gravitational pull of roughly 0.001 Earth's gravity, enough to slightly bend the path of dust particles but not enough to prevent their escape altogether. Additionally, the jet would interact with the solar wind, a stream of charged particles flowing from the sun. This interaction could cause the jet to curve slightly or develop a faint secondary tail, though such effects might be too subtle to detect without high-resolution imaging. The solar wind's influence is not trivial. It travels at speeds of up to 800 kilometers per second and can ionize particles in the jet, creating a faint glow that could be detectable with the right instruments. Despite these challenges, the directed jet theory remains compelling because it aligns with known cometary behavior. Comets are inherently asymmetric objects with irregular shapes and uneven distributions of ices. This asymmetry can lead to localized outgassing, producing jets that are strong enough to alter the comet's spin and even its orbit over time. For example, Comet 103P Hartley 2's jets were powerful enough to cause the comet to wobble as it rotated, a phenomenon captured by NASA's Deep Impact spacecraft during its flyby. If 3I Atlas has a similar jet, it could explain not only the anti-tail, but also any unusual patterns in the comet's brightness or motion. Some comets, like 19P Borrelli, have exhibited jets that were so powerful they carved deep pits into the nucleus, leaving behind craters up to 300 meters wide. Such features, if present on 3I Atlas, could provide strong evidence for the jet theory. However, without direct observations of the nucleus or detailed measurements of its rotation, this theory remains speculative. Observation. The anti-tail's linear structure persists despite expected rotational smearing. Interpretation. This suggests that if a jet is responsible, the nucleus must be rotating slowly, or the jet must be aligned with the spin axis. Speculation. Could 3I Atlas have an unusually slow rotation rate, or is there another explanation for the jet's stability? Could the jet be intermittent, only appearing stable due to the limits of our current observations? Unknown. The nucleus's rotation rate or vent location. The possibility of multiple vents contributing to the anti-tail's appearance. To test this theory, astronomers would need to study the anti-tail in greater detail, looking for variations in brightness or structure that could hint at the jet's behavior. High-resolution imaging, perhaps with the Hubble Space Telescope or the James Webb Space Telescope, could reveal subtle changes in the jet's trajectory or composition. For instance, Hubble's Wide Field Camera 3 can resolve features as small as 0.04 arc-seconds, which could be enough to detect the slight curvature of a jet interacting with the solar wind. Spectroscopic observations could also help by identifying the gases and dust within the jet, providing clues about the nucleus's chemistry. Infrared spectroscopy, for example, could detect the presence of water ice, carbon dioxide, or other volatiles, while ultraviolet observations could reveal the ionization state of the jet's particles. If the jet theory is correct, these observations could offer unprecedented insight into the dynamics of cometary outgassing and the internal structure of comet nuclei. However, if the yuan jet proves elusive, astronomers may need to consider even more exotic explanations for the mysterious anti-tail. The possibility of multiple jets working in tandem, or even a vent that pulsates in intensity, could add layers of complexity to this already intriguing theory. Part 6. The Interstellar Factor. 3I Atlas didn't form in our solar system. It originated in an entirely different stellar environment, potentially billions of kilometers from a different star. Its trajectory doesn't trace back clearly to any nearby stellar system, meaning it's been wandering through interstellar space for potentially millions of years. This journey alone is astonishing, a voyage through the vast emptiness between stars, where temperatures plummet to just a few degrees above absolute zero, and the ambient density is less than 1 atom per cubic centimeter. During this time, 3I Atlas would have been exposed to cosmic rays, high-energy particles that penetrate deep into its icy nucleus, potentially altering the chemistry of its frozen materials. But wherever it formed, the conditions were different. The stellar nebula around its parent star had a different composition, different temperatures, and different dynamics. This means 3I Atlas's internal makeup could be significantly different from the comets we've studied for centuries. It might have ices we rarely see, dust grains with unusual mineralogy, and structural properties that differ from solar system comets. For example, the dust grains in 3I Atlas could include silicates enriched with elements like magnesium or iron, reflecting the unique mineralogy of its birthplace. Its ices might contain higher proportions of hydrogen cyanide, HCN, or other complex organic molecules which are key precursors to amino acids and other building blocks of life. Previous spectroscopic observations of 3I Atlas detected carbon-based molecules in its coma, including molecular carbon chains and possibly carbon monoxide in higher abundances than typical for solar system comets. Carbon monoxide is interesting because it's a volatile ice, sublimating at much lower temperatures than water. If 3I Atlas formed in an exceptionally cold region of its natal stellar system, it could have incorporated large amounts of carbon monoxide and other supervolatile ices that solar system comets don't contain in such abundance. For instance, in the outer reaches of a protoplanetary disk, where temperatures can drop below 30 Kelvin, carbon monoxide and even molecular nitrogen, N2, can freeze onto dust grains, becoming trapped in the comet's icy matrix. Why does this matter? Because supervolatile ices change the activity profile. A comet rich in carbon monoxide would start outgassing much farther from the Sun than a water-dominated comet. It would remain active longer as it moves away from the Sun because those volatiles continue sublimating even at lower temperatures. For comparison, solar system comets like Halley and 67P, Churyumov-Gerasimenko typically become active around 3 to 4 astronomical units, AU, from the Sun, driven primarily by water ice sublimation. 3I Atlas, however, might begin outgassing as far out as 10 AU or more, where sunlight is too faint to significantly heat water ice. This extended activity could create a coma and tail that evolve in unexpected ways, persisting even as the comet recedes from the Sun, and the gas pressures generated by sublimating carbon monoxide are different from water, affecting how dust particles are ejected and accelerated. Carbon monoxide sublimates at around 20-30 Kelvin, while water ice requires temperatures above 150 Kelvin. This lower sublimation threshold means that carbon monoxide can drive activity even in the frigid outer solar system, producing a faint but persistent coma. The resulting dust tail might appear more diffuse and spread out, as the lower gas pressures eject particles more gently. Compared to the violent outgassing of water vapor, this could explain why 3I Atlas's tail structures appear unusual, with a broader, more feathery appearance than the sharp, well-defined tails of many solar system comets. Observation: 3I Atlas contains higher abundances of carbon monoxide and other volatile ices, Interpretation: the presence of these supervolatiles suggests that 3I Atlas formed in a colder region of its natal stellar system than most solar system comets. This could indicate an origin in the outer reaches of a protoplanetary disk, where temperatures were low enough to freeze out carbon monoxide, molecular nitrogen, and other highly volatile compounds. Such conditions are more common around low-mass stars, like red dwarfs, which have cooler protoplanetary disks compared to stars like our Sun. A speculation. If 3I Atlas did originate around a red dwarf, its composition might reflect the unique chemistry of such systems. Red dwarfs are the most common type of star in the Milky Way, making up about 75% of all stars. However, their protoplanetary disks are thought to be less efficient at forming large, rocky planets due to their lower temperatures and slower accretion rates. As a result, comets and other icy bodies might play a more dominant role in the delivery of volatiles and organics too. Any potential habitable zones in these systems. 3I Atlas could provide a rare glimpse into the composition and dynamics of comets from such environments, offering insights into the potential for habitable worlds around the galaxy's most abundant stars. Unknown. The full extent of its exotic composition and how it affects tail structures. While carbon monoxide and other supervolatiles have been detected, the full inventory of 3I Atlases. ICES remains uncertain. Future observations, particularly in the infrared and microwave regions of the spectrum, could reveal the presence of additional exotic compounds, such as methanol, formaldehyde, or even complex hydrocarbons. These molecules could further enhance the comet's activity, creating a rich chemical factory as they break down under solar radiation. Additionally, the unusual mineralogy of its dust grains might influence how they scatter and reflect light, producing subtle color variations in the tail that could be studied with high-resolution imaging. As 3I Atlas continues its journey through the solar system, it carries with it the story of its interstellar voyage and the remnants of its distant origin. By studying this enigmatic object, scientists hope to unravel the mysteries of comet formation in other stellar systems, shedding light on the diversity of planetary environments. Across the Cosmos. Part 7. The Exotic Composition Hypothesis. The exotic composition hypothesis is compelling. It doesn't require abandoning known physics. It just requires acknowledging that the material inventory of 3I Atlas might be outside the range we've thoroughly characterized. Our models of cometary behavior are built on thousands of observations, but those observations are all of solar system comets. For over 2 centuries, scientists have studied the composition and behavior of comets within our solar neighborhood. Halley's Comet, for example, has been observed and documented since 240 BCE, providing a wealth of data on periodic comets. The European Space Agency's Rosetta mission spent over a decade chasing Comet 67P Churyumov-Gerasimenko, delivering the Philae lander to its surface in 2014 and collecting unprecedented data on its composition and behavior. But 3I Atlas is different. We've studied exactly 2 interstellar comets in detail. Before this one, 2I Borisov, detected in August 2019, was the first interstellar comet to show clear signs of outgassing, a process where ices sublimate directly into gas as the comet approaches the Sun. Borisov's coma, the nebulous envelope around its nucleus, was rich in carbon monoxide and water vapor, but its faintness prevented detailed analysis of its structure. Meanwhile, 1I Oumuamua, the first observed interstellar object, was already On its way out of the solar system when it was discovered in 2017, its cigar-like shape and lack of outgassing left more questions than answers, hinting at the diversity of interstellar objects, but offering little in the way of compositional details. The exotic composition hypothesis provides a mechanism for ongoing activity. Supervolatile ices could be feeding the antitail, replenishing particles, and maintaining structure against dispersion. Supervolatile ices, such as molecular hydrogen, nitrogen, or carbon monoxide, have much lower sublimation points than water ice, which dominates most solar system comets. These ices could remain active even at greater distances from the Sun, explaining 3I Atlas's unusual behavior. For instance, the New Horizons spacecraft observed nitrogen ice outgassing on Pluto's surface during its 2015 flyby, despite the dwarf planet's average distance of 39.5 astronomical units from the Sun. It also explains the dust composition. Unusual carbon compounds might be cohering differently, clumping into larger aggregates, or maintaining density through processes we don't fully understand. Carbon-rich compounds such as polycyclic aromatic hydrocarbons, PAHs, have been detected in the tails of comets and are thought to contribute to their optical properties. These complex molecules could behave unpredictably. Under the influence of solar radiation and wind, potentially explaining the unusual persistence of 3I Atlas's antitail. But even exotic composition has limits. Supervolatile ices can explain sustained activity, and unusual dust can explain some optical properties. But can they explain the sharpness and persistence of the antitail structure against 18 days of dispersion? Can carbon monoxide outgassing alone maintain a columnated beam of particles? When radiation pressure, solar wind turbulence, and orbital mechanics are all trying to spread them out, comets typically lose up to 1% of their mass with each orbit due to outgassing and dust loss, a process that contributes to their eventual disintegration. For an interstellar object like 3I Atlas, which will not return to the inner solar system, this process should be even more pronounced. This is where even the exotic composition theory runs into the same problem as the conventional theories. It provides a mechanism for ongoing activity, but activity alone doesn't guarantee structure. You need a focusing mechanism, a reason why the particles stay in a narrow beam rather than puffing out in all directions like they do in the broader dust tail. The solar wind, a stream of charged particles flowing from the Sun, exerts significant pressure on cometary tails, often causing them to fan out into broad, diffuse structures. Yet 3I Atlas's antitail defies this expectation, maintaining its coherence despite the relentless forces working against it. Observation: the antitail's structure persists despite the dispersion forces. Unknown: the focusing mechanism maintaining the narrow beam. The mystery deepens as we consider the implications of 3I Atlas's behavior. If exotic composition is the answer, it suggests that interstellar objects may be far more diverse than we previously imagined. Each new discovery, from 1I Oumuamua's cigar-like shape to 2I Borisov's faint outgassing, challenges our understanding of how comets form and evolve. 3I Atlas, with its persistent antitail and unusual dust composition, may be the key to unlocking a new chapter in cometary science. But for now, the focusing mechanism remains elusive, a puzzle that continues to defy easy explanation. As researchers around the world analyze the data pouring in from observatories, the debate over 3I Atlas's nature intensifies. Some argue that its behavior could be explained by a combination of factors, an interplay of super volatile ices, unusual carbon compounds, and perhaps even magnetic interactions with the solar wind. Others propose that we may be witnessing something entirely new, a class of interstellar objects that defy our current. Models. Whatever the answer, 3i Atlas stands as a testament to the vastness and unpredictability of the cosmos, a reminder that even as we strive to understand the universe, it continually surprises us with its complexity. Part 8. The Uncomfortable Edge. We're now at the uncomfortable edge of this investigation, where natural explanations, while possible, require stacking assumptions and fortunate circumstances to fully account for the observations. It's not that any single assumption is unreasonable. Large particles exist, jets exist, exotics exist, but when you need all of them together in specific configurations at specific times to explain one feature of one comet, the explanation starts feeling less like a robust model and more like a tailored fit. And that's when scientists start asking the next level question, not because they want to abandon natural explanations, but because intellectual honesty requires considering all possibilities when the standard models struggle. To illustrate the complexity, consider the behavior of comets like Borisov. Its trajectory and composition have been meticulously studied, revealing a mix of familiar volatiles like carbon monoxide and water ice, but also hints of unexpected materials. If Borisov's anti-tail particles are indeed moving at velocities that defy conventional outgassing models, it forces us to confront the limits of our understanding. The Hubble Space Telescope, which has been instrumental in tracking Borisov, captured images showing particles ejected from the comet's nucleus at velocities that seemed inconsistent with typical outgassing. Mechanisms. While some researchers attribute this to the unique composition of the comet, others are less convinced. Enter Avi Loeb, the Harvard astrophysicist known for publicly advocating that the scientific community should be more open to considering non-natural explanations for anomalous objects. In a November 16th of Medium article, Loeb suggests cautiously that if the anti-tail particles are moving at velocities significantly higher than what natural outgassing can produce, that would require an explanation beyond sublimation pressure. Natural outgassing from comets accelerates particles to speeds of a few hundred meters per second, sometimes up to a kilometer per second, in very active jets. If spectroscopy measures velocities in the range of multiple kilometers per second, that starts looking less like gas pressure and more like something else. Loeb suggests that one possibility worth investigating is whether the velocity could be explained by artificial propulsion, a directed energy source. Loeb's proposal is not without precedent. In 2017, the first interstellar object ever observed, Oumuamua, exhibited peculiar behavior that led some scientists to speculate about its origins. Its elongated shape, tumbling motion, and unexpected acceleration as it left the solar system sparked debates about whether it could be an artificial object. While most researchers favored natural explanations such as outgassing from hidden ices, Loeb argued that the lack of visible cometary activity made these explanations less compelling. He proposed that Oumuamua might be a defunct piece of alien technology, a light sail propelled by solar radiation pressure. Though controversial, his hypothesis highlighted the need for scientists to remain open-minded in the face of unprecedented data. The controversy surrounding Oumuamua serves as a cautionary tale for Borisov. If Borisov's anti-tail particles are moving at velocities that cannot be explained by natural mechanisms, the implications are profound. It would challenge our understanding of cometary behavior and force us to consider alternative explanations, no matter how uncomfortable they may be. Loeb's suggestion of artificial propulsion is just one of many possibilities, but it underscores the importance of rigorous observation and analysis. The scientific community must remain vigilant, ensuring that no stone is left unturned in the quest for truth. Observation. High-velocity particles in the anti-tail could suggest artificial propulsion. Interpretation. The presence of particles moving at velocities exceeding natural outgassing limits could indicate an alternative propulsion mechanism. This interpretation aligns with Loeb's hypothesis that such velocities might be explained by a directed energy source, potentially of artificial origin. However, this interpretation remains highly speculative and requires extensive further investigation. Unknown. Precise velocity measurements of the anti-tail particles. The quest to understand Borisov's anti-tail is far from over. Researchers are currently analyzing data from ground-based observatories and space telescopes to obtain more precise measurements of the particles' velocities. If these measurements confirm the presence of high-velocity particles, it will mark a turning point in the investigation. The scientific community will be faced with a choice: either refine existing models to account for the new data or entertain the possibility of alternative explanations. Whatever the outcome, the pursuit of knowledge demands that we confront the uncomfortable edges of our understanding, pushing the boundaries of what we think is possible. In the meantime, the debate surrounding Borisov's anti-tail serves as a reminder of the challenges and opportunities inherent in studying interstellar objects. These celestial wanderers offer a glimpse into the mysteries of the universe, forcing us to question our assumptions and expand our horizons. As we continue to explore the cosmos, we must remain open to the unexpected, embracing the discomfort that comes with pushing the limits of our knowledge. For it is in these moments of uncertainty that true discovery begins. Part 9. The Velocity Question. Loeb's hypothesis highlights a critical gap in our current data. We don't yet have precise velocity measurements of the anti-tail particles. Spectroscopy can fill this gap. When particles move, their light gets Doppler shifted, blue shifted if they're moving toward us, red shifted if they're moving away. By taking a spectrum of the comet's tails and analyzing the precise wavelengths of emission lines from ions and reflected light from dust, astronomers can calculate how fast those particles are moving and in what direction. This isn't a rough estimate. With good spectrographs, you can measure velocities to within tens or hundreds of meters per second. That precision is enough to distinguish between natural outgassing and something more energetic. Imagine the scene in an observatory high in the Chilean Andes, where the air is thin and the sky is clear for over 300 nights a year. Astronomers are huddled over screens, adjusting the spectrograph's settings to capture the faint light from Oumuamua's tails. The instrument is a marvel of engineering, capable of resolving wavelengths with an accuracy of 1 part in 100,000. As the data streams in, the team watches for subtle shifts in the spectral lines, knowing that even a slight deviation could reveal the velocity of the particles with stunning precision. The stakes are high. A single measurement could rewrite our understanding of this interstellar visitor. The observatory's dome hums softly as it rotates to track the comet, its mirrors reflecting the faint glow of distant stars. If the spectroscopy shows that anti-tail particles are moving at speeds consistent with sublimation pressure, that strongly supports the natural explanations. It would mean the particles were ejected by gas pressure from the nucleus and are now coasting gradually, slowing due to radiation pressure and spreading due to velocity dispersion. This is the expected result, and it would point towards the exotic ice hypothesis or the massive particle population theory as the most likely explanation. For example, if the particles are moving at a leisurely 100 meters per second, it would align with the behavior of comets in our own solar system, where outgassing typically produces velocities in this range. However, if the velocities are significantly lower, it could suggest a nucleus with unusual properties, such as a higher density or a different composition than typical comets. In 2018, the European Southern Observatory detected Oumuamua accelerating at a rate consistent with cometary outgassing, but the lack of a visible coma or tail raised questions. Precise velocity measurements of its anti-tail particles could resolve this mystery. But if the spectroscopy shows higher velocities that can't be explained by gas pressure alone, that opens new questions. What mechanism is accelerating those particles? Radiation pressure is always present, but it's a gentle force, not sudden acceleration. Solar wind can transfer momentum, but again, the accelerations are gradual. If particles are moving significantly faster than sublimation plus radiation pressure can account for, you'd need an additional energy source. For instance, velocities exceeding 500 meters per second would be highly unusual for a natural comet and would require an explanation beyond conventional outgassing. This could point to an artificial mechanism, such as a propulsion system or an intentional ejection of material. In our solar system, the fastest observed cometary outgassing, such as that of Comet Hartley 2, reaches velocities of around 150 meters per second, far below this threshold. Consider the implications if the particles are moving at 1,000 meters per second or more. That would be unprecedented for a comet, and it would force astronomers to confront the possibility of an artificial origin. Such velocities are more commonly associated with spacecraft or deliberate ejection mechanisms, not natural processes. The data would spark intense debate within the scientific community, as researchers would scramble to find alternative explanations or confirm the presence of technology. Loeb's hypothesis would suddenly move from the realm of speculation to a testable theory, with profound implications for our understanding of extraterrestrial life. The idea of an interstellar object with such high-velocity particles would challenge existing models of cometary behavior and force a re-evaluation of Oumuamua's origins. In the quiet of the observatory, the astronomers would lean back in their chairs, staring at the numbers on their screens. The velocity measurements would flicker into view, each digit a potential game changer. If the particles are moving at breakneck speeds, the team would feel a mix of exhilaration and unease. Exhilaration at the prospect of discovering something extraordinary, and unease at the thought of what it might mean. The room would fall silent as the data settles in, the weight of the findings pressing down on everyone present. Outside, the Andean night would stretch endlessly, the stars above unchanged, but the understanding of the universe below forever altered. Observation. Precise velocity measurements are needed to distinguish between natural and artificial explanations. Unknown. The mechanism accelerating the anti-tail particles if velocities are higher than expected. Speculation. If the velocities are significantly higher than expected, it could indicate an artificial mechanism, such as propulsion or intentional ejection. The implications of such a discovery would be staggering, potentially redefining our understanding of life beyond Earth. However, even if the velocities align with natural explanations, the data would still provide valuable insights into the composition and behavior of interstellar comets, furthering our knowledge of these elusive objects. The velocity question is not just a technical detail. It is a gateway to answering one of humanity's most profound questions. Are we alone in the universe? If the measurements point to an artificial origin, it would mark the first time in history that humanity has detected evidence of extraterrestrial technology. Part 10, December 19th. The Countdown. December 19th, 2025 is not just a date, it's a scientific opportunity. On that day, 3I Atlas makes its closest approach to Earth, about 1.8 astronomical units away, roughly 270 million kilometers. That's not close by inner solar system standards, but in astronomical terms it's close enough to matter. Every kilometer of distance affects the resolution and signal strength of the observations we can make. Between now and that date, every major telescope that can be scheduled is being tasked with looking at this object. The priority is spectroscopy, high-resolution spectroscopy designed to measure the velocities of particles in the antitail and other tail structures. These particles, ejected from the comet's nucleus as it heats up under the sun's glare, carry critical information about the comet's composition and history. Each tail structure, from the dust tail to the ion tail, tells a different part of the story. The antitail, for instance, is a rare and fleeting feature that forms when Earth passes through the plane of the comet's orbit, allowing us to see dust particles that are normally obscured by the glare of the comet's head. The observatories participating in this campaign include the European Southern Observatory's Very Large Telescope, VLT, which has some of the best spectrographs in the world. The VLT's high accuracy. Radial Velocity Planet Searcher, HARPS, and Ultraviolet and Visual Echelle Spectrograph, UVES instruments are particularly well suited for this task, capable of detecting minute shifts in the wavelengths of light emitted or absorbed by the comet's particles. These shifts, known as Doppler shifts, reveal the velocities of the particles, which in turn tell us about the forces acting on them: gravity, solar radiation pressure, and magnetic fields, ground-based. Networks like the Las Cumbres Observatory, with telescopes around the globe, can track the comet continuously, ensuring no outburst or sudden change goes unnoticed. Las Cumbres' 24-hour coverage is vital for monitoring the comet's dynamic behavior, as comets are notoriously unpredictable. Their telescopes, though smaller than giants like the VLT, are agile and numerous, providing a steady stream of data that complements the deeper, more detailed observations of larger instruments. Space-based platforms like Hubble, if observing time is allocated, could provide unparalleled resolution. Orbiting above Earth's atmosphere, Hubble avoids the distortions caused by turbulence and can capture images with stunning clarity. Its Advanced Camera for Surveys, ACS, and Wide Field Camera 3, WFC3, are particularly suited for studying comets, offering a wide field of view that can capture the entirety of 3I Atlas's sprawling tails. Even smaller observatories and amateur networks are contributing imaging data, providing continuous monitoring that helps identify short-term changes or outbursts. Amateur astronomers, equipped with increasingly sophisticated gear, have become vital partners in modern astronomy. Their round-the-clock vigilance ensures that transient events, like sudden brightening or tail disconnections, are documented and shared with the scientific community. These contributions are not just supplementary, they are essential. In 2020, for instance, amateur astronomers were the first to detect the dramatic fragmentation of Comet Atlas C 2019-Y4, providing critical data that professional observatories used to refine their models of comet behavior. This is a coordinated effort, and the data is being shared in near real time through astronomical telegrams and circulars so that observers worldwide can refine their strategies based on what others are seeing. The International Astronomical Union's Central Bureau for Astronomical Telegrams, (IBAT), serves as a hub for these rapid communications, disseminating observations and analyses within hours of their submission. This real-time sharing allows observatories to adjust their instruments and focus on emerging features, maximizing the scientific return of the campaign. For example, if one observatory detects a sudden increase in gas emission from the comet, others can quickly train their spectrographs on the same region to capture the event in detail. This collaborative approach ensures that no opportunity is wasted, as the comet's behavior can change dramatically in just a few hours. By mid-December, preliminary results from spectroscopy should start appearing in astronomical telegrams, brief announcements that share key findings. Before full papers are written, these telegrams are the first glimpse into the comet's secrets, offering tantalizing clues about its composition and history. They might reveal, for instance, the presence of complex organic molecules or the ratio of isotopes like deuterium to hydrogen, which can indicate the comet's origin in the outer solar system. By early January, enough data will have been analyzed to start drawing firm conclusions. Researchers will begin piecing together the story of 3I Atlas, using the spectroscopic data to model its trajectory, determine its age, and even infer the conditions in the early solar system when it formed. By late January or February, expect to see papers submitted to journals presenting comprehensive analysis of 3I Atlas's behavior during this apparition. These papers will undergo peer review, a rigorous process where other scientists scrutinize the findings to ensure their validity. Once published, they will become part of the permanent scientific record, available to researchers worldwide. That timeline means we're weeks away from having answers, not months. The scientific process is moving quickly because the target is time-sensitive. Comets fade as they move away from the sun, and the opportunity to gather high-quality data is limited. 3I Atlas is no exception, as it rounds the sun and begins its journey back to the outer solar system. Its tails will diminish, and its surface activity will slow. By March 2026, it will be too faint for most telescopes to study in detail. This makes the December 19th window critical. The data gathered during this period will shape our understanding of comets for years to come, providing insights into the building blocks of planets and the delivery of water and organic materials to the early Earth. Observation. December 19th is the optimal observation window for 3I Atlas. Unknown, the results of spectroscopic velocity measurements and other data. Speculation. The findings from 3I Atlas could challenge existing models of comet formation and behavior, potentially rewriting our understanding of these icy visitors from the edges of the solar system. Part 11. The Observational Campaign. The observation campaign for 3I Atlas is more than just spectroscopy. Photometry, measuring brightness changes over time, will reveal the particle production rate and possibly the nucleus rotation. A brightening antitail would suggest increasing activity, while a dimming antitail would indicate the persistence we've seen is reaching its limit. Periodic variations, if they match a rotation period, would support the directed jet hypothesis, showing that the jet rotates with the nucleus and we're seeing brightness cycles as it points toward and away from us. Imagine the nucleus as a spinning top, ejecting material in a focused stream that sweeps across our line of sight like a lighthouse beam, causing measurable fluctuations in brightness. These fluctuations could be subtle, perhaps a mere 0.5 magnitude change, but they would be enough to confirm the nucleus's rotation period, which might range from 6 to 20 hours based on similar comets. Photometry will also help us understand the size and behavior of the dust particles. Smaller particles, less than a micron in diameter, scatter sunlight more efficiently, creating a brighter anti-tail. Larger particles, however, contribute more to the infrared thermal emission as they absorb and re-radiate sunlight. By combining visible and infrared photometry, scientists can estimate the size distribution of the particles, which in turn reveals the mechanisms by which they were ejected from the nucleus. Was it a violent outburst, shattering the comet's surface and releasing a broad range of particle sizes, or a gentler process, lifting only the finest dust? Morphological tracking is also critical. High-resolution imaging through late November and December will map how the anti-tail structure evolves day by day. Does it maintain its sharp profile? Or does it start to blur and widen? The antitail initially stretched across an arc of roughly 10 degrees in the sky, a staggering sight visible even in small telescopes. However, as the comet approaches perihelion, the solar radiation pressure that shapes the antitail will intensify, potentially causing it to broaden and diffuse. This evolution could be dramatic. The antitail might spread to an arc of 15 degrees or more, creating a spectacular but ephemeral display. Does the antitail break into filaments or segments, suggesting particle streams with different velocities? Filaments, thin and wispy, could indicate that the nucleus is ejecting material in spurts, each with slightly different speeds and directions. These filaments might stretch and twist as they interact with the solar wind, creating a dynamic, ever-changing structure. Alternatively, if the anti-tail remains smooth and unbroken, it would suggest a steady, continuous outflow of material, perhaps from a single active region on the nucleus. Does the anti-tail remain straight, or does it curve, revealing the orbital mechanics of the particles more clearly? A perfectly straight anti-tail would imply that the particles are moving in the plane of the comet's orbit, unaffected by external forces. However, a curved anti-tail would hint at the complex interplay between the particles and the solar environment. The curvature could be caused by the solar wind deflecting the particles, or by the orbital motion of the comet itself, creating a spiral pattern as it moves through space. Multi-wavelength observations add another layer. Looking at the comet in radio wavelengths can detect specific molecules like carbon monoxide and methanol that emit radio photons when excited by sunlight. For instance, the detection of carbon monoxide at a wavelength of 2.6 millimeters would indicate the presence of ices sublimating directly from the nucleus. Methanol, on the other hand, might be detected at 7.0 millimeters, suggesting a rich, organic chemistry at play. These molecules are like fingerprints, revealing the composition of the comet's ices and the processes driving its activity. Infrared observations reveal thermal emission from dust grains, telling us about their temperature and composition. For example, silicate grains, common in cometary dust, emit strongly at wavelengths around 10 microns. By measuring the intensity and shape of these emission features, scientists can determine the mineralogy of the dust, providing clues about the conditions in the early solar system when the comet formed. If the infrared spectrum shows strong silicate features, it would suggest that the dust is primitive and unaltered, preserving a record of the comet's origins. Ultraviolet observations highlight ion populations and can map the solar-wind interaction. Ions like carbon monoxide, CO+, and water, H2O+, glow brightly in the ultraviolet, tracing the regions where the solar wind strips electrons from neutral molecules. These ions form a plasma tail that stretches millions of kilometers into space, glowing faintly under the relentless bombardment of solar radiation. By tracking the motion of these ions, scientists can map the magnetic field lines of the solar wind as they drape around the comet, creating a natural laboratory for studying plasma physics. Each wavelength provides a different piece of the puzzle, and together they build a comprehensive picture of what's happening. If radio observation shows strong carbon monoxide emission from the direction of the anti-tail, that supports ongoing sublimation of volatile ice's feeding. The structure. If they don't, that suggests the anti-tail is primarily dust, and the particles were expelled earlier and are now just coasting. The absence of carbon monoxide emission would indicate that the comet's activity has slowed, leaving behind a trail of inert dust that continues to drift through space. Observation. Multi-wavelength observations will provide a comprehensive picture of 3I Atlas's activity. Unknown. The results of photometry, morphological tracking, and multi-wavelength data. Interpretation. The behavior of the anti-tail, whether it brightens, dims, or changes shape, will reveal the physical processes driving the comet's activity. Speculation. If the anti-tail remains sharp and straight, it could imply a steady, directed outflow of material, perhaps from a single active region on the nucleus. Conversely, a broadening or curving anti-tail would suggest more. Complex dynamics, such as variable outgassing or interactions with the solar wind. The possibility of detecting specific molecules like carbon monoxide or methanol in the radio spectrum could provide definitive evidence for the comet's composition and activity. If these molecules are absent, it would challenge current theories about the comet's behavior and force scientists to reconsider their models. The upcoming observations will not only answer these questions but also raise new ones, deepening our understanding of cometary dynamics and the origins of the solar system. Part 12. The Philosophy of Investigation. The upcoming observations are not just about 3I Atlas. They're about how science investigates mysteries. They're about the process of gathering evidence, testing hypotheses, and refining understanding. And there's a demonstration that we live in an era where these investigations happen in real time, where dedicated observers and professional researchers collaborate globally, and where interested people like you can follow along as discoveries unfold. This isn't a mystery that will be solved in secret and announced years later. This is science happening now, and the next 4 weeks are the critical window. Imagine the scale of this collaboration. Astronomers across continents from the Atacama Desert in Chile to the snow-capped peaks of Mauna Kea in Hawaii are coordinating their efforts. Telescopes like the Very Large Telescope, VLT in Chile, with its 4 8.2-meter mirrors, and the Keck Observatory in Hawaii, equipped with adaptive optics to correct for atmospheric distortion, are being pointed toward the same enigmatic object. Data streams from these observatories will converge, creating a mosaic of information that will be analyzed by teams of scientists working around the clock. Researchers will pore over spectra, light curves, and polarization data, searching for subtle clues that could unlock the object's secrets. This Real-time collaboration is unprecedented in scale and speed, a testament to the interconnectedness of modern science. What each outcome would mean is worth considering. If the data confirms natural processes, exotic ices, large particles, sustained jets, 3i Atlas becomes a case study in the diversity of interstellar objects. It refines our understanding and improves our ability to predict and interpret future interstellar visitors. For instance, the detection of exotic ices could reveal new chemical pathways that occur only in the extreme conditions of interstellar space. Large particles might suggest unique formation processes that challenge our current models of planetary system evolution. Sustained jets could offer insights into the dynamics of outgassing, a phenomenon observed in comets but rarely studied in interstellar objects. These findings could inspire new research directions, such as developing advanced spectroscopic techniques to detect trace compounds in interstellar objects. If the data reveals something that doesn't fit current natural models, if velocities or structures defy known mechanisms, then the scientific conversation shifts. More exotic natural processes would be proposed and tested. For example, the discovery of anomalous velocities could point to previously unknown gravitational interactions or the influence of unseen companions. Structures that defy known mechanisms might suggest the presence of magnetic fields or other forces that are not fully understood. These possibilities would push the boundaries of our knowledge, forcing scientists to rethink fundamental assumptions about the universe. The discovery of unexpected phenomena could also lead to the development of new theoretical frameworks, as researchers attempt to reconcile observations with existing physics. And if those still don't suffice, the door opens to truly novel explanations, which would be extraordinary but also extraordinarily exciting because they'd mean we're learning something fundamentally new about how the universe works. The stakes are high, but so is the potential for breakthroughs. Consider the impact of past discoveries that defied initial explanations. The detection of cosmic microwave background radiation in 1964 confirmed the Big Bang theory, revolutionizing our understanding of the universe's origins. The observation of gravitational waves in 2015 validated Einstein's general theory of relativity, opening new avenues for studying black holes and neutron stars. Each of these moments reshaped our understanding of the cosmos, and 3i Atlas could be the next pivotal chapter in this ongoing story. The potential for new knowledge is immense, and the scientific community stands ready to embrace whatever revelations come to light. The upcoming observations are not just about resolving the mystery of 3i Atlas. They're about the human endeavor to understand the universe. They're about the relentless pursuit of knowledge, the joy of discovery, and the collective effort to push the frontier of science further. Whether the answers are familiar or groundbreaking, the process itself is a testament to the power of curiosity and collaboration. The search for answers has always driven humanity forward, from the earliest stargazers to the scientists of today. This quest is not just about uncovering truths, but also about inspiring future generations to explore, question, and dream. Observation. The scientific process is actively investigating 3i Atlas in real time. Unknown. The final explanation for the anti-tails behavior. Interpretation. The current theories range from natural phenomena to more exotic possibilities, each with profound implications for astrophysics. Speculation. If the anti-tails behavior defies all known explanations, it could signal the presence of new physics, potentially rewriting textbooks and inspiring future generations of scientists to explore the unknown. Part 13. The Broader Context. 3i Atlas is one object, but it represents the beginning of a new field in astronomy, the study of interstellar objects as a population, not as individual curiosities. When Oumuamua raced through our inner solar system in October 2017, it was the first confirmed interstellar object humanity had ever detected. Before that moment, interstellar visitors were theoretical. We knew they had to exist. Stellar systems form with far more comets and asteroids than they retain, and gravitational interactions eject countless objects into the void between stars. But theory is one thing, detection is another. Oumuamua was a shock for multiple reasons. Its shape appeared elongated, possibly cigar-like or pancake-like depending on interpretation. Its light curve, the way its brightness changed as it tumbled, was unlike any asteroid or comet previously observed, and it exhibited a small but measurable non-gravitational acceleration, a tiny push that couldn't be fully explained by solar radiation pressure alone. This acceleration, though minute, amounted to a deviation of roughly 30 meters per second squared over its observed trajectory, sparking debates about possible causes, from outgassing to more exotic explanations. Its origin remains enigmatic, with some models suggesting it may have been wandering through interstellar space for hundreds of millions of years. Before its encounter with our Sun, Oumuamua's discovery triggered a global effort to scour existing telescope data for signs of similar objects that might have been overlooked in the past. These searches turned up no confirmed interstellar objects in archival data, reinforcing the rarity of such detections with our current technology. However, statistical models based on Oumuamua's trajectory and the sensitivity of modern surveys estimate that there could be thousands of Oumuamua-like objects passing through the inner solar system at any given time, though most are too small or too distant to detect with current instruments. Its detection was only possible because of its relatively close approach to Earth, coming within 0.25 astronomical units, about 23 million kilometers, before hurtling back into interstellar space. The Pan-STARRS telescope in Hawaii, which spotted Oumuamua, is credited with revolutionizing the search for near-Earth objects, but even it can only detect objects like Oumuamua when conditions align perfectly. Tuai Borisov arrived in August 2019 and was different from Oumuamua in almost every way. It looked like a comet, with a visible coma and clear tail, and its behavior matched cometary models reasonably well. Its chemistry was unusual in some respects, with different ratios of carbon monoxide to water than solar. System comets typically show, but not so unusual that it defied explanation. Tuai Borisov became the proof of concept that interstellar comets exist and can be studied with the same tools we use for solar system comets. But it was faint throughout most of its passage, limiting the detail we could extract. High-resolution spectroscopy was challenging, and nucleus imaging was impossible. It remained a point source. We learned, but we were still data-limited. Its peak brightness reached only magnitude 15, making it about 25,000 times fainter than the faintest stars visible to the naked eye. Observatories like the Hubble Space Telescope and the Very Large Telescope in Chile were pushed to their limits to gather what data they could before Borisov faded from view. Unlike Oumuamua, which likely originated from a star system hundreds of light-years away, Tuai Borisov's trajectory suggested it came from a much closer stellar neighborhood. Its velocity and path indicated it may have been ejected from a red dwarf star system within 50 light-years of our own. This proximity raises the tantalizing possibility that future interstellar objects results could be traced back to specific stars, allowing us to study not just the objects themselves, but also the environments that shaped them. Borisov's cometary nature also provided a glimpse into the composition of other star systems. Its higher carbon monoxide content compared to solar system comets hints at a colder formation environment, perhaps in the outer reaches of its parent system, where volatile ices like carbon monoxide are more likely to form and persist. 3I Atlas, the third confirmed interstellar object, combines elements of both Oumuamua and Borisov while offering new mysteries. Its discovery in June 2024 was met with excitement and trepidation. Unlike its predecessors, Atlas was brighter and closer when first detected, allowing for more detailed observations. Preliminary data suggests it has a hybrid composition with characteristics of both an asteroid and a comet. Its light curve shows subtle variations that hint at a complex, irregular shape, and its spectrum reveals traces of both rocky and icy materials. Atlas also exhibits non-gravitational acceleration, though the cause remains unclear. Some researchers speculate it may be due to outgassing from pockets of volatile material embedded in its surface, while others suggest it could be the result of interactions with the solar wind. The study of interstellar objects like Atlas is not just an academic pursuit. It has profound implications for our understanding of planetary formation and the potential for life beyond our solar system. Every interstellar object is a fragment of another. Stars' history, a messenger from distant worlds. By examining their compositions and trajectories, we can infer the conditions of their birthplaces. For example, the abundance of certain isotopes in an interstellar object could reveal whether its parent star was rich in heavy elements, a characteristic often associated with the potential for rocky planet formation. Similarly, the presence of organic compounds could hint at the building blocks of life being scattered throughout the galaxy. Observation: 3I Atlas is the third confirmed interstellar object, providing unprecedented observational detail. Its hybrid composition and non-gravitational acceleration make it a unique case study. Unknown: the full extent of the interstellar object population and its diversity. Current estimates based on detection rates suggest there could be one interstellar object passing through the inner solar system every year, though most go undetected due to their faintness and speed. Future surveys, such as the Vera C, Rubin Observatory's Legacy Survey of Space and Time, LSST, are expected to revolutionize our ability to detect and study these objects. The LSST, slated to begin full operations in the mid-2020s, will scan the entire visible sky every few nights, potentially detecting dozens of interstellar objects during its 10-year mission. Each new detection will add to our growing catalogue of these cosmic travelers, helping us piece together the larger story of our galaxy's history and the exchange of material between stars. As we look to the future, the study of interstellar objects promises to reshape our understanding of the universe. These objects are more than just curiosities. They are ambassadors from distant star systems, carrying with them the stories of their origins. With every new detection, we inch closer to unraveling the mysteries of how planets form, how materials are exchanged across the cosmos, and whether the conditions for life might exist beyond our solar system. The journey of 3I Atlas is just one chapter in this unfolding narrative, a testament to the boundless potential of exploration and discovery. Part 14. The Future of Interstellar Object Studies. The study of interstellar objects is about to explode. The Vera Rubin Observatory, currently under construction in Chile, will begin full operation soon. It's a survey telescope designed to scan the entire visible sky every few nights, detecting transient events and moving objects. Its sensitivity and field of view are optimized to catch faint, fast-moving objects, exactly the profile of interstellar visitors. Current estimates suggest Rubin will detect 1 to 2 interstellar objects per month once it's fully operational. That's not a typo. From 3 confirmed interstellar objects in human history, we're about to jump to dozens per year. Within a decade, we could have a catalogue of hundreds, providing statistical samples large enough to characterize the population, identify subtypes, and build robust models of interstellar object properties. Imagine the scale of this transformation. Astronomers will no longer be limited to studying a handful of interstellar objects. Instead, they will have a rich dataset that allows for detailed comparisons and analyses. This influx of data will enable the development of sophisticated classification systems, much like the taxonomies used in biology or geology. For instance, interstellar objects could be categorized based on their size, composition, velocity, and trajectory. These categories might reveal distinct formation histories or origins, offering insights into the diverse processes at work in distant star systems. The Vera Rubin Observatory's capabilities extend far beyond mere detection. Its advanced instrumentation will allow for detailed observations of these objects as they traverse our solar system. Spectroscopic analysis could reveal the chemical composition of their surfaces, shedding light on the conditions in their originating systems. Photometric measurements will track their brightness variations, offering clues about their shapes, rotational periods, and even internal structures. Additionally, high-resolution imaging might capture features like jets, outgassing, or fragmentation events, providing a dynamic view of these objects in motion. That flood of data will contextualize 3i Atlas. Right now, it's one of 3. An unusual behavior makes it an outlier. But if Rubin detects 10 more objects showing similar anti-tail persistence, suddenly 3i Atlas isn't an outlier. It's part of a category. If no other object shows this behavior, then 3i Atlas truly is unique, and understanding why becomes even more critical. Either outcome advances knowledge, and the rapid pace of discovery means we won't wait decades for answers. The next few years will transform interstellar object science from a niche field studying rare curiosities into a mature discipline with datasets, classification schemes, and predictive theories. The future of interstellar object studies also lies in international collaboration. Observatories around the world will complement the Vera Rubin Observatory's findings, providing additional perspectives and data. For example, the European Space Agency's Gaia mission, which is mapping the Milky Way in unprecedented detail, could help pinpoint the trajectories of interstellar objects with extraordinary precision. Meanwhile, ground-based facilities like the Atacama Large Millimeter Sub-Millimeter Array, ALMA in Chile, could study the thermal properties of these objects, revealing their internal temperatures and compositions. Beyond observation, the next decade will likely see the development of new technologies specifically designed to intercept and study interstellar objects up close. NASA's proposed comet Interceptor mission, for instance, aims to launch a spacecraft that could be redirected to rendezvous with an interstellar object if one is detected on a suitable trajectory. Such missions could provide the first close-up images and direct measurements of these enigmatic travelers, revolutionizing our understanding of their nature and origins. The societal impact of these discoveries cannot be overstated. Interstellar objects are messengers from distant stars, carrying information about the diversity of planetary systems and the processes that shape them. As our knowledge of these objects grows, so too will our appreciation for the complexity and interconnectedness of the universe. Schools, museums, and public outreach programs will incorporate these findings into their curricula, inspiring the next generation of scientists and explorers. By observation, the Vera Rubin Observatory will revolutionize the study of interstellar objects. Unknown, the full diversity and behavior of the interstellar object population. Speculation, interstellar objects may reveal profound insights into the formation of planetary systems, the distribution of life-supporting elements across the galaxy, and even the possibility of extraterrestrial life itself. In this new era of discovery, every interstellar object becomes a potential breakthrough. Each detection, each measurement, each mission brings us one step closer to unraveling the mysteries of the cosmos. The future of interstellar object studies is not just a story of scientific progress. It is a story of humanity's enduring curiosity and our relentless pursuit of knowledge beyond the boundaries of our world. Part 15. The Final Countdown. We're 32 days from the closest approach, and the mystery of 3i Atlas is far from solved. But the countdown has begun. Every major telescope that can be tasked is being pointed at this comet. From the massive 8.2-meter Subaru telescope in Hawaii, perched atop the dormant volcano Mauna Kea, where its altitude offers unparalleled clarity, to the cutting-edge ALMA array in Chile's Atacama Desert, which can detect faint molecular emissions with its 66 high-precision antennas. The observation campaign is coordinated, comprehensive, and designed specifically to answer the questions the anti-tail raises. Astronomers are working around the clock, sifting through terabytes of data, comparing spectral signatures, and modeling trajectories. By early January, we'll have preliminary results, raw and unfiltered, offering the first glimpses into the comet's true nature. By late January or February, comprehensive. Analysis will be published, scrutinized, and debated in scientific journals and conferences. The mystery has a timer on it, and that timer is counting down. The global effort to study 3i Atlas is unprecedented in scale. Over 150 researchers from 23 countries are collaborating, sharing data in real time across continents. Supercomputers such as NASA's Pleiades supercomputer, which can perform over 7 quadrillion calculations per second, are simulating the comet's behavior, crunching billions of calculations to test theories about its origin and composition. NASA's Deep Space Network, a system of giant radio antennas normally used to communicate with spacecraft like Voyager 1, which is currently over 15 billion miles from Earth, has been repurposed to track the comet's trajectory with unparalleled precision. The European Space Agency's Gaia satellite, which maps the positions of over 1 billion stars with an accuracy of up to 24 micro-arc seconds, is being used to pinpoint the comet's path through the Milky Way. This isn't just a scientific endeavor, it's a global event, a testament to humanity's collective curiosity and capacity for cooperation. Regardless of the outcome, 3i Atlas has already accomplished something scientifically important. It's challenged our models, forcing astronomers to reconsider assumptions about post-perihelion behavior in comets, especially interstellar comets with potentially exotic compositions. For example, the comet's unusual brightness and persistent anti-tail have led some researchers to propose that it might contain higher than expected amounts of heavy elements like iron or nickel, which could explain its resilience to solar radiation. Others suggest that its nucleus might be more porous than typical comets, allowing it to release gases in a way that defies conventional models. Either way, these questions are pushing the boundaries of our understanding. It's provided a case study that will be referenced in future research on cometary dynamics and interstellar object characterization. For decades, comets were seen as relatively simple objects, dirty snowballs with predictable behavior. But 3i Atlas has shown us that even these familiar celestial bodies can surprise us. Its anti-tail, for instance, has persisted for over 100 days, defying predictions that it should have dissipated weeks ago. This challenges our understanding of how solar wind and radiation interact with cometary material, and it could lead to new insights into the physics of cometary tails. Every observation of 3i Atlas adds to a growing database that will inform future missions, like the European Space Agency's planned Comet Interceptor, designed to rendezvous with an interstellar object in the 2030s. The Comet Interceptor, currently slated for launch in 2029, will wait at the Sun-Earth Lagrange point L2, 1.5 million kilometers from Earth, ready to intercept a long-period comet or interstellar object once one is discovered. And it's demonstrated that the field of interstellar object studies is not just theoretical. It's observational, active, and producing puzzles that require serious investigation. The discovery of Oumuamua in 2017 was a turning point, but 3i Atlas takes it further. Unlike Oumuamua, which was detected only after it had passed its closest approach to the Sun, 3i Atlas was identified early, giving scientists a rare opportunity to study an interstellar object in real time. This has allowed for unprecedented coordination among observatories, with ground-based telescopes working in tandem with space-based instruments to capture every detail. The result is a dataset that will keep scientists busy for years, unraveling the secrets of this enigmatic visitor. For instance, the Hubble Space Telescope, which has been operational for over 30 years and orbits the Earth every 97 minutes, has been used to capture high-resolution images of 3i Atlas, revealing subtle changes in its appearance over time. Whether the final explanation is mundane or extraordinary, the process of investigating this comet is advancing our understanding of how comets work, what interstellar visitors are like, and how science approaches anomalies. Already, the preliminary data has sparked debates about the comet's origin. Some researchers argue that its trajectory suggests it came from a binary star system, where gravitational interactions could have ejected it into interstellar space. Others point to its composition, which hints at a formation process unlike anything in our own solar system. These discussions are not just academic exercises, they're shaping our understanding of the cosmos and our place within it. For example, the discovery that 3i Atlas might contain unusual isotopes of elements like oxygen or carbon could provide clues about the conditions in its natal star system, offering insights into the diversity of planetary formation processes across the galaxy. There's something deeply human about following a mystery like this in real time. We're not reading about a discovery made decades ago and neatly summarized in textbooks. We're watching science happen. We're seeing the observations come in, the discussions unfold, the hypotheses proposed and tested. On December 15th, for instance, a team of astronomers using the Hubble Space Telescope detected a sudden spike in the comet's brightness, leading to a flurry of speculation about potential outgassing events or fragmentation. Within hours, researchers across the globe were analyzing the data, proposing explanations and planning follow-up observations. This isn't science as a finished product, its science as a living, breathing process. The excitement is palpable, reminiscent of the global effort to track asteroid Apophis in 2004, when initial calculations suggested a small but alarming chance of impact with Earth, sparking an international campaign to refine its orbit and rule out the threat. You now know what comets normally do. You know why anti-tails are temporary. You know the timeline of 3I Atlas's behavior, and why each checkpoint where it should have faded becomes another data point in favor of something unusual happening. For example, on November 23rd, the comet passed through a region of space known for its dense interstellar dust. Normally, this would have dimmed its brightness, but 3I Atlas seemed unaffected, further fueling theories about its unusual composition. You understand the competing theories and where each one is strong or weak. Some argue that the comet's anti-tail is the result of a unique interaction between its material and the solar wind, while others suggest it could be evidence of a recent collision with another object. Each theory has its proponents and detractors, and each new. Observation brings us closer to the truth. The debate is reminiscent of the ongoing discussions about the composition of Pluto's atmosphere, which was long thought to be primarily nitrogen, but has recently shown hints of complex organic compounds, challenging our understanding of the outer solar system. You're equipped to follow the December observations and interpret what they mean when the results are announced. On December 28th, the comet will pass within 0.25 astronomical units of Earth, providing an unprecedented opportunity to study it up close. Telescopes around the world will be trained on it, capturing high-resolution images and spectroscopic data. Amateur astronomers will join in, sharing their observations on social media and contributing to the global effort. You'll be able to watch this unfold in real time, understanding the significance of each new finding and appreciating the challenges faced by the scientists working to solve the puzzle. For example, amateur astronomers equipped with modest telescopes have already captured stunning images of 3I Atlas, highlighting the democratization of science in the modern era, where anyone with the right tools and curiosity can participate in cutting-edge research. That's the value of going deep on a topic like this. Surface-level coverage tells you a weird comet has 3 tails, and leaves it there. Deep investigation tells you why that's weird, what the implications are, what we're doing to investigate, and what the possible answers might be. It transforms you from a headline consumer into someone who actually understands the science, someone who can evaluate claims and recognize when evidence supports a conclusion versus when it's still uncertain. For instance, when a headline proclaims that 3I Atlas is definitely an alien spacecraft, you'll know to look beyond the sensationalism, examining the data and weighing the evidence. You'll understand that extraordinary claims require extraordinary proof, and you'll be able to judge whether that proof exists. The process is akin to the scrutiny applied to the detection of phosphine gas in the clouds of Venus in 2020, which initially sparked excitement as a potential sign of life, but was later met with skepticism, as further analysis questioned the validity of the findings. Final thought: 3I Atlas is teaching us that the universe still holds surprises, that our models are good, but not perfect. On December 12th, a simulation predicted that the comet's anti-tail should have faded by now, but observations showed it was still visible, forcing researchers to re-evaluate their assumptions, that there's always more to learn, and every time we look closely at something we assumed we understood, we find surprises. 3I Atlas is this year's surprise. there will be more. In 2024, the Vera C. Rubin Observatory will come online, scanning the entire sky every few nights and likely discovering dozens of interstellar objects in the process. Each one will offer new insights, new mysteries, and new opportunities to expand our understanding of the cosmos. The Rubin Observatory, equipped with the world's largest digital camera, a 3.2 gigapixel behemoth capable of capturing images with stunning detail, will revolutionize our ability to detect and study transient phenomena like comets and asteroids. That's the essence of exploration. Not knowing what you'll find, but being ready to learn when you find it. In the coming weeks, 3i Atlas will make its closest approach to Earth, giving us a fleeting chance to study it in detail before it recedes into the depths of interstellar space. We may never see it again, but the knowledge it leaves behind will shape our understanding of the universe for generations to come. So, keep looking up, keep questioning, and keep digging deeper than the surface allows, because that's where the real understanding lives.